Hello everyone and welcome to McLean 360. Alright, so in this video I want to solve a question to illustrate the concept of stress, the normal stress and then the shearing stress. Alright, so let's go through the problem together. So in this problem we have a hydraulic cylinder CF. So this is the hydraulic cylinder which partially controls the position of rod DE. So that is rod DE, and then it has been locked in the position below. Okay, so as it stands now, in this position, it has been locked. Okay. All right, then our task is to okay, he said member BD is 5 by 8 inch. So member BD is this member over here. Okay. And then it's connected to the vertical rod by a 3 on 8 inch diameter bolt. Okay. Now our task is to find the average shearing stress in the bolt and then the bearing stress as C in member BD. All right. So this question is kind of difficult, but if you look at it carefully, you realize that it's very much simple. But then the first thing to do is to draw the free body diagram. So let's look at how the free body diagram looks like. So in the free body diagram, the first thing to look at is BCD. So if you look at BCD is something like this. Okay. After getting BCD, you realize that at point C here, this point C over here is some sort of a joint. So we can label this C as a pin with two reactions, CX and then CY. Okay. Now after getting the CX and the CY, we can go forward and say that okay, let me bring it down. So let's say C is somewhere here. So I have CY, then I have CX. The distance all the way here is 4 inch, and then the distance all the way from here to the top is 7 inch. All right. Now point B is here, and then point D is here. Standing at point B, what do you see? At point B, we have this member here, but then this member is actually a two-force member. Okay, so when we see a two-force member, it means tension or compression. So basically, we can sort of look at this as just a force which is in this direction. Okay, so it's a two-force member. That's what we are trying to say. So we can label the force which is in that AB with just this. Okay, all right. And then at D, there is this force here which makes an angle of 75 with the horizontal. Now it looks like this. So this is the force, and this is 75, and this one is 400 pounds. All right. So this is the free body diagram of the rod, or no, the system actually. So we are choosing BCD, and then we are looking at the free body diagram on BCD. Okay. So the first thing to do is to find our forces, and then we will find the shear stresses. So this problem is a typical statics problem. So we have to use equilibrium of a rigid body. All right. So for a rigid body to be in equilibrium, what do we know? We know that if a rigid body will be in equilibrium, then summation of forces and moment must be what? Zero. Okay. So then let's start with summation of forces along the x. So I'm going to sum forces along the s. Every force in this direction is positive. Let's look at the here. You would realize I want to resolve this. So I want to resolve FAB into x and y. But FAB is acting along this line. So let's say that you have a triangle, over here. The side is 8.2 and the height is 8. So what is the distance? That distance will be so let's pick our calculators. 8 squared plus 1.8 squared. So you are going to get 8.2. Oh, in fact, this is 1.8 and the 8.2 is here. All right. So that is it. If I want to resolve that force, it's going to be the horizontal component, which is 1.8, divided by the hypotenuse, which is 8.2. Then I multiply by the force. Okay. But then, because the force is coming this way, the s component is going to be negated. So minus. Okay. And then cx. All right. And then we need to also look at the x component. For this one, it's going to be straightforward. 400 cosine 75. So I'm just going to resolve this into x and y. And the x component is cosine and it's positive. Should be equal to 0. Okay. So let's call this, maybe let's simplify it first. So what is 1.8 divided by 8.2? That's going to be 0.219. So let's say 0.22. So minus 0.22 FAB plus CS should be equal to 400 cosine 75. So 103.528. 103.528. So minus 103.528. Call this equation 1. Again, let's sum forces in the y. Every force going up is positive, should be 0. The y component of FAB will come down and it's going to be minus. This time around, we are going to use the vertical side. 8 over the hypotenuse, which is 8.2, and then multiplied with the force. Then we will come to CY. Should be, oh no, we need to add. So the y component of the 400 pound force will come down. So it's going to be negative 400 sine 75. Okay, to be 0. So okay, what is 8 on 8.2? That is 0.976, or let's say 0.98 FAB plus CY should be equal to 400 sine 75. 386.37. 386.37, equation 2. So we have 3 unknowns and then we have 2 equations. This tells us that we need to get one more equation, which will come from moment. Okay, so let's some moment about C. All right, so now this is what we are going to do. We will take each force and then take the moment from C. Starting from FAB, we have 2 forces. Okay, so let me bring it down here so that you appreciate it. This is what we are saying. You have something like this here, okay? And then you have x component here, and then y component here. Now you are taking moment from C, and this distance is 4. So if you take the x component, the perpendicular distance will be this. But then if you take the y component, the perpendicular distance will rather be this side. Okay, so here is 4. Don't forget that this is 4 and it makes an angle 20. So it means that this 20 is here. Okay, so 4 cosine 20, 4 sine 20. All right, so it's going to be from the s component, it's going to be clockwise, and then the moment is given by 1.8 over 8.2 FAB, which is the force. Then I'll multiply the force by the distance, which is 4 sine 20. But then if you use the y component, this one, the distance will rather be 4 cosine 20. But then the moment is going to cause anti-clockwise moment. So it's going to be 8 over 8.2 FAB cosine, 4 cosine 20. So we are done with FAB part. Then we will move to this one, the last part at D. So we have this one here, 103.53, and then we have 386.37, and then we are taking the moment all the way from C. So what do we have to do is that we have to resolve C, and then this is what we get. Or we can either do this. Maybe let me do it this way. All right. So if I am to use the, okay, this is 20. If I am to use the horizontal component, then the perpendicular distance is this side, okay, which is what? 7 cosine, 7 sine 20. But then if I use this side, it's going to be 7 cosine 20, which will be perpendicular to this. Okay. All right. So um the x component will be plus 103.53. Then I'll multiply it with the sine 20 part. Then for the s component, so this one is going to give us clockwise. But for the y component, about c, yeah, that one is also going to be clockwise. Okay. So that one is also going to be clockwise. So it's going to be 386.37. Then I multiply this by 7 cosine 20. This is equal to 0. So let's solve for FAB. Okay. Now, this is what we are about to do. We need to solve for FAB. So solving for FAB, we can say that FAB into bracket, so 1.8 over 8.2 multiplied by 4 sine 20, and then minus 8 divided by 8.2, and then multiply by 4 cosine 20. That is FAB, right? Oh man, multiplied. And what is that? So that is minus 3.366, or let's say minus 3.367. So minus 3.367 FAB. And then let's combine this and then this. You know, this one is plus. Okay. What do we have? So for that one, it's going to be 103.53 multiplied by 7 sine 20 plus 386.37 multiplied by 7 cosine 20. So that is what we get. Oh no, supposed to be point here. You have to be very careful with your computation. All right. So 2789.35. 2789.35. If I do this and equate this to 0, then FAB will be what? Minus 2789.35 divided by minus 3.367. And what is that? So divided by 3.367. So 828.437. 828.437 pound. Okay. So since we know FAB, we can find CX. All right. So CX is going to be minus 103.528 plus 0.22 FAB, which is 828.437. Okay. So that is CS. Let's calculate it. So minus 103.528 plus 0.22 into 828.437. And what is that? So CX, as we see, is nothing but 78.34. So CX 78.72, or let's say 73 pound. And then CY, so CY will also be what? So CY will be 386.37. We are using the equations we have already developed, plus 0.98 FAB, which is 828.437. Having done this, CY will then be 386.37 plus 0.98 into 828.437, right? And what is it? 1198.24 pound. Okay. So we have FAB, we have CX, and then we have CY. Okay. So from here, we can then go straight forward and then solve. Okay. So C, let's find C. The magnitude of C will be the square root of CS squared plus CY squared, which is what? So CX is 78.73 or 73 squared 1198.24 squared. And what is that? So the magnitude of C, or the reaction at C, is 78.73 squared plus 1198.24 squared. And what is that? Almost, okay, so 1200.8 pound. Okay, so that is the magnitude of the reaction at C. All this while, we have been doing statics. So now let's branch into strength of materials, because now without the statics, we will not be able to get the reaction forces. But now that we know the reaction forces, we can now solve it. Interestingly, the boat is connected at C. Look at the question. The question said that I have a boat here. Look at this. This is the actual, the CF is the hydraulic cylinder. And then you can see that it is connected by a boat. All right. So the question is saying that this member BD here, this member BD here is connected by CF with what? A boat. So that is the boat here. Is that clear? Now this boat is having a diameter of what? 3 by 8 inch. So we have to find the average shearing stress in this boat. All right. So let's do that. The average shearing stress is what? So that is what we are looking for. Shearing stress, tau. So shearing stress, tau, is given by the load, or the shear force, divided by the area. So in this case, the load becomes the C, because that is the force which is acting at the C where the boat is. And then the diameter of the boat was 3 by 8. So let's quickly do this. It's going to be 1200.8 divided by pi 3 over 8 squared divided by 4. So I can bring the 4 here. And that will be the shear stress in the boat. All right. So let's calculate it together. It's going to be 1200.8 multiplied by 4. Then I divide this by pi multiplied by 3 by 8 squared. Okay. So that is the shear stress I'm getting. So 108.72. So maybe we can say that this is actually 108.72 KSI. So that's the shear stress in the member. Okay. All right. So all right. So then it's going to be I think it's 10. Sorry. 10.87 KSI. Okay. Part B says that we should calculate the bearing stress as C in member BCD. Okay. So the bearing stress is going to be so at C. So the bearing stress is sort of the normal stress actually. But then the shearing stress is the stress due to shear from the boat. But for the normal stress, we are going to use this area here from the member BD, which is 3.8. So, okay. So for the bearing stress from the boat is going to be the load, which is the same force divided by the area. But this time around is going to be 1200.8 multiplied by 4 divided by pi. Oh, sorry. This time around, we are going to use the normal stress. Therefore, you will include the diameter or the thickness of member BD. This member, okay, you will include it because the question said the bearing stress as C in member BD. So there is a thickness of member BD. Therefore, if I multiply that thickness of member BD by the diameter of the boat, I will get an area. And that area is actually the required area for the bearing stress. Okay. So it's going to be 3 on 8 multiplied by 5 on 8. Okay. That gives us 1200.8 multiplied by 4. And then you divide this by 3 on 8 and then multiply by 5 on 8. Oh, then you don't need to multiply by 4 because it's just the force over that area. So all what we are trying to say is that the bearing stress is the load divided by the thickness multiplied by the diameter. That's all what we are trying to say. So what is it then? So 1, 2, 3. So 20.5 KSI approximately. So that is the bearing stress in the boot. So this problem has been solved. Thank you very much for watching.